Welcome to the Basics of Chemistry. Please open up your textbook to page 254 and let's begin. Why study chemistry? Cosmetologists should have a thorough understanding of chemistry because without the understanding of basic chemistry, you won't be able to use professional products effectively and safely. With understanding chemistry, you're able to troubleshoot and solve common problems you're going to encounter with your chemical services, which makes up a large portion of your service revenue. After reading these sections, you're going to be able to list the difference between organic and inorganic chemistry. How to recognize the science of chemistry and the influence in cosmetology. Please highlight. Chemistry is the science that deals with composition, structures, properties of matter, and how matter changes under different conditions. Please highlight. Organic chemistry is the study of substances that contain the element carbon. I'll repeat. Please highlight. Organic chemistry is the study of substances that contain the element carbon. And a highlighting. All living things that were once alive, whether they're plants, animals, whatever, they contain carbon. Organic compounds contain other elements like nitrogen and oxygen, but it's that bond between the carbon and hydrogen that makes it organic. Organic substances contain both carbon and hydrogen that can burn. Although the term organic is often used to mean safe or natural because it's an association with living things such as foods and food ingredients, not all organic substances are actually natural, healthy, and safe. You're going to be surprised to learn that gasoline, motor oil, plastics, synthetic fibers, pesticides, and fertilizers are all actually organic substances. All hair color products, chemical texturizers, shampoos, conditioners, styling aids, nail enhancements, and skincare products are organic chemicals. So always remember the word organic, as applied to chemistry, does not mean it's natural or healthy. It means the material contains both carbon and hydrogen from either a natural or synthetic source. Moving on to page 255. Please highlight. Inorganic chemistry is the study of substances that do not contain the element carbon, but may contain the element hydrogen. Please continue highlighting. Most inorganic substances do not burn because they do not contain carbon. End of highlighting. Inorganic substances are not and never were alive. Metals, minerals, glass, water, substances are not and were never alive. Metal, minerals, glasses, and air are inorganic substances. Pure water and pure oxygen are inorganic, yet they're an essential part of life. Hydrogen peroxide, hydrogen hair relaxers, titanium dioxide, and zinc oxide in the sun protection creams are inorganic substances. Defining matter. Please highlight. Matter is a substance that occupies space and has mass. Please continue highlighting. All matter has physical and chemical properties that exist in the form of a solid, liquid, or gas. End of highlighting. Since matter is made from chemicals, everything is made out of matter is a chemical. Matter has physical properties that we can touch, taste, smell, or see. In fact, everything that you can touch and everything you can see, with the exception of light and electricity, is matter. All matter is made up of chemicals. You can see visible light and light that electrical sparks create, but these are not made of matter. Light and electricity forms are energy, and energy is not matter. Please highlight. Everything known to exist in the universe is either made of matter or energy. There are no exceptions to this rule. And a highlighting. Please star that. Either made of matter or energy. Energy does not occupy space or have mass. Energy is discussed further in the next chapter, Basics of Electricity. This chapter is dedicated strictly to matter. Moving on to elements. Please highlight. An element is the simplest form of chemical matter. Please continue highlighting. It cannot be broken down into a simpler substance without a loss of identity. Continue highlighting. There are 118 known elements today, and of those 98 occur naturally and the rest are produced by synthetic methods of nuclear reactions. End of highlighting. All matter in the universe is made up of these elements, and they have their own distinct physical and chemical properties. Each element is identified by a letter or symbol, such as O for oxygen, C for carbon, H for hydrogen, N for nitrogen, S for sulfur. Symbols for all elements can be found on your periodic table of elements in chemistry textbooks, or even just by looking up on the internet. Moving on to page 256, atom. Please highlight. An atom is the basic unit of matter with a nucleus at the center that's surrounded by negatively charged electrons. Please continue highlighting. These electrons move around the nucleus orbits. Please continue highlighting. The nucleus consists of protons, subatomic particles with a positive charge. And the neutrons, continue highlighting, are subatomic particles with no charge. And the number of protons determines that element. End of highlighting. Atoms cannot be divided into simpler substances by ordinary chemical means. You can see it on figure 12-1. It shows the atomic structure of a carbon with 6 protons, 6 neutrons, and the nucleus, and the 6 electrons actually in orbit. Moving on to molecules. Just as words are made by combining letters, molecules are made by combining atoms. Please highlight. A molecule is a chemical combination of 2 or more atoms in definite fixed proportions. End of highlighting. For example, water is made from hydrogen atoms and oxygen atoms. Carbon dioxide is made from carbon atoms and oxygen atoms. Atmosphere's oxygen and other chemical substances such as nitrogen and water vapor make it to the air you breathe. Please highlight. This type of oxygen is called an elemental molecule. A molecule containing 2 or more atoms of the same element, in case of this oxygen, definite fixed proportions. It is written as O2. Please continue highlighting. Ozone is another elemental molecule made up of oxygen. End of highlighting. Ozone is a major component of smog and can be super dangerous. It contains 3 atoms of the element of oxygen and is written as O3. You can see on figure 12-2 an atomic oxygen. When 2 are added, 2 oxygens are added, it's O2. When 3 are added, it's O3. Compound molecules, also known as compounds, are a chemical combination of 2 or more atoms of different elements in definite fixed proportions. Sodium chloride, NaCl, it would be your abbreviation on your periodic table, is actually common table salt. It's an example of compound molecules. Each sodium chloride molecule contains 1 atom of the sodium and 1 atom of the element chlorine. Moving on to page 257. Let's learn about our states of matter. All matter exists in one of these 3 physical forms. Please highlight. All matter exists in one of these 3 physical forms. Solid, continue highlighting, liquid, and gas. Please continue highlighting. These 3 forms are called states of matter. Please star states of matter. End of highlighting. Matter becomes one of these states depending on the temperature. Like many of these substances, water H2O can exist in 3 states of matter, depending on its temperature. A great example of this is water changes according to how the temperature changes, but it's still always water. Please highlight. When water freezes, it turns to ice. Continue highlighting. When ice melts, it turns back to water. Please continue highlighting. When water boils, it turns to steam. And a highlighting. When steam cools, it turns back to water. The water stays the same chemical. Please highlight. The water stays the same chemical, but becomes a different physical form. When one chemical changes its state of matter, it's called a physical change. You can see on figure 12-4 your solid form listed there, your liquid form listed below, and your gas form listed on the bottom. Physical and chemical properties of matter. Every substance has unique properties that allow us to identify it. These 2 types of properties are physical and chemical. Please highlight. Physical properties are characterized that can be determined without a chemical reaction that do not involve a chemical change or in that substance. You can see on table 12-1 a great example of solid, liquid, and gas. The solid is rigid, has a fixed shape and volume. Example would be a brush or a roller. A liquid has a definite volume, but it will always take shape to the container that it's in. A good example would be bleach, shampoo, hair color, or water. Lastly, your gas. It has no fixed volume or shape. It takes shape and volume to its container. It can never be liquid at a normal temperature or pressure. An example in our industry would be a propellant in hairspray, mousse, and propane. Moving on to page 258. Physical properties include color, solubility, odor density, melting point, boiling point, hardness, and glossiness. As described above, the state of matter that a substance becomes is an example of a physical property. Let's move on to chemical properties. Please highlight. Chemical properties are characteristics that can only be determined by the chemical reaction and chemical change of the substance, and a highlighting. Examples of the chemical properties include the ability to iron to rust, wood to burn, or the hair to change color through the use of hair color and hydrogen peroxide. Please ensure that you have highlighted. Chemical properties are characteristics that can only be determined by a chemical reaction and a chemical change in the substance, and a highlighting. Let's talk about our next learning outcome. Summarizing in your own words the ability of oxidation reduction reactions. Physical and chemical changes. Matter can be changed in 2 different ways: physical forces and physical changes, and in addition, chemical reaction and chemical changes. Please highlight. A physical change is a change in the form or physical properties of a substance without a chemical reaction or the creation of a new substance, and a highlighting. No chemical reactions are involved in a physical change and no new chemicals are formed. Solid ice undergoes a physical change when it melts into water and then converts into steam when heat is applied. A physical change occurs when nail polish is applied onto the nails and the solvent evaporates, forming a layer or film on the nail. A chemical change, please highlight. A chemical change is a change in the chemical composition or makeup of the substance. This change is caused by chemical reactions that create new chemical substances, usually by combining or subtracting certain elements, and a highlighting. Those new substances have different chemical and physical properties. For example, a chemical change in the oxidization of hair color. Please star oxidization. Please highlight. The term oxidization refers to a chemical reaction that combines a substance with oxygen to produce oxide, and a highlighting. Another example of oxidization of melanin pigments in hair is by hydrogen peroxide when you're actually lightening it. Moving on to oxidation reduction, also known as redox. Please highlight. Oxidation reduction, also known as redox, is a chemical reaction in which oxidization and the reduction take place at the same time. And a highlighting. When oxygen is chemically combined with a substance, the substance is oxidized. When the oxygen is chemically removed from a substance, it is called reduced. Moving on to page 259. Please highlight. An oxidizing agent is a substance that actually releases oxygen. And a highlighting. Hydrogen peroxide, H2O2, which can be thought of as water with an extra atom of oxygen, is an example of an oxidizing agent. Please highlight. A reducing agent is a substance that adds hydrogen to the chemical compound or substance and subtracts oxygen from that compound. And a highlighting. When hydrogen peroxide is mixed with an oxidative hair color, oxygen is subtracted from the hydrogen peroxide and the peroxide is reduced. At the same time, oxygen is added to the hair color and the hair color is oxidized. In this example, hair color is the reducing agent. So far, we've considered oxidization as only the additional oxygen and reduction for the loss of oxygen. Although the first known oxidization reactions involve oxygen, many oxidization reactions don't even involve oxygen. Oxidation also results from a loss of hydrogen, and reduction and results from the addition of hydrogen. Redox reactions are also responsible for the chemical changes created by hair colors, lighteners, permanent wave solutions, thioglycol, and acid neutralizers. These chemical services would not be possible without oxidization reduction or redox reactions. Under certain circumstances, these chemical reactions can release a significant amount of heat. Please highlight. These types of chemical reactions are called exothermic reactions. And a highlighting. In fact, all oxidization reactions are exothermic reactions. An example of an exothermic reaction is a nail product that hardens to create nail enhancements. Exothermic reactions occur, but usually clients cannot feel the heat actually being released. Please highlight. Combustion. That is rapid oxidization of a substance accompanied by a production of heat and light. And a highlighting. Lighting a match is an example of rapid oxidization. Oxidization requires the presence of oxygen, and this is the reason there cannot be fire without air. Let's learn how to explain the differences between pure substances and physical mixtures. On the bottom of page 259, please know all matter can be classified as either a pure substance or a physical mixture, which is a blend. A pure substance, please highlight. A pure substance is a chemical combination of matter in definite fixed proportions. Pure substances have unique properties. And a highlighting. Aluminum foil is an example of a pure substance. It only has the atoms of the element aluminum. Most substances do not exist in a pure state. Please know that. Most substances do not exist in a pure state. Air contains many substances, including nitrogen, carbon dioxide, and water vapor. This is an example of a physical mixture. Please highlight. A physical mixture is a physical combination of matter in any proportion. The properties of the physical mixture are combined properties of the substance in the mixture. Please continue highlighting. Salt water is a physical mixture of salt in the water in any proportion. These properties of salt and water are the properties contained in salt. Salt water is salty and wet. Most of these products cosmetologists and nail techs are going to use are physical mixtures. You can see an example on figure 12-8. Moving on to page 260. Solutions, suspensions, and emulsions. Solutions, suspensions, and emulsions are all physical mixtures. The differences among solutions, suspensions, and emulsions are determined by the types of substances, the size of particles, and the solubility of those substances. Please highlight. A solution is a stable mixture. Please highlight. A solution is a stable physical mixture of two or more substances in a solvent. Please continue highlighting. The solute is a substance that is dissolved in a solution. Continue highlighting. The solvent is the substance that dissolves the solute and makes the solution. For example, when the salt is dissolved in water, salt is the solute and water is the solvent. End of highlighting. Water is known as the universal solvent because it has the ability to dissolve more substances more than any other solvent. Please look at Table 12-12, the differences between pure substances and physical mixtures. This would be a great one to actually add to your flashcards. Pure substances, they are united chemically, while a physical substance is only united physically. A pure substance is definite and fixed proportions. A physical mixture has any proportion. A pure substance is unique chemical and physical properties. A physical mixture is combined chemical and physical properties. A pure substance has salt and pure distilled water, and they're examples of a pure substance. While a physical mixture, salt water, is a physical mixture. Moving on to page 261. All liquids are either miscible or immiscible. Please highlight. Miscible liquids are mutually soluble, meaning that they can be mixed together to form a clear solution. Water and alcohol are examples of miscible liquids, as in nail polish remover. And a highlighting. When these substances are mixed together, they will stay mixed, forming a solution. Solutions contain small particles that are invisible to the naked eye. Solutions are usually transparent, although can be colored. They do not separate when they're left still. Again, salt water is an example of a solution with the solid dissolved in the liquid. Water is a solvent that dissolves the salt, the solute, and then holds the solution. Immiscible. Please highlight. Immiscible liquids are not capable of being mixed together to form a stable solution. Water and oil are examples of immiscible liquids. They just don't mix. These substances can be mixed, and a highlighting, These substances can be mixed together but will separate when they're left sitting still. When immiscible liquids are combined, they form suspensions. Suspension. Please highlight. They are unstable physical mixtures of undissolved particles in a liquid. Compared with solutions, suspensions contain larger and fewer miscible particles. Continue highlighting. These particles are generally visible to the naked eye, but do not seem large enough to settle quickly at the bottom. And a highlighting. Suspensions are not usually transparent and may be colored. They are unstable and they separate over time, why some lotions and creams can separate in the bottle and need to be shaken before you use them. Please highlight. Another example of a suspension is glitter in nail polish. It can separate from the polish. And a highlighting. The suspension will separate when it is left sitting still and must be always shaken before using. Calamine lotion and nail polish are other examples of suspension. Let's move on to emulsion. Please highlight. An emulsion is an unstable physical mixture of two or more immiscible substances. Immiscible as they normally won't stay blended, plus a special ingredient called an emulsifier. Please star this and know it and highlight. An emulsifier is an ingredient that brings two normally incompatible materials together and binds them together into a uniform, fairly stable blend. And a highlighting. Emulsions are considered to be a special type of suspension because they can separate, but the separation usually happens really slowly over a long period of time. An example of emulsion is hand lotion. a properly formulated emulsion stored underneath ideal conditions. They can be stable for up to 3 years. Since conditions are rarely ideal, all cosmetic emulsions should be used within 1 year of their purchase. Always refer to your product's instructions and cautions for specific details. Moving on to page 262. Another great table, table 12-13. I want you to copy or make these into your flashcards. This will help you retain the information. A solution is miscible. Suspensions, it's lightly miscible. And emulsions are immiscible. Solutions, there's no surfactant. Suspensions have no surfactant, but an emulsion has a surfactant. A solution has small particles, while a suspension has larger particles. Same with an emulsion. A solution has a stable mixture. A suspension has unstable, temporary mixture. And your emulsions are limited stability through the emulsifier. Solutions are usually clear. A suspension is typically cloudy. And an emulsion is usually a solid color. Solutions, for example, solution of a nail primer. A suspension would be nail polish, glitter in nail polish. An emulsion, a good example, would be shampoos, conditioners, and hand lotions. This is a summary of the differences among solutions, suspensions, and emulsions. Moving on to surfactants. On page 262, please highlight. Surfactants are substances that allow oil and water to mix or emulsify. They're one type of emulsifier. And to highlight it. The term surfactant is a contraction for the surface of active ingredients, substances that allow oil and water to mix or emulsify. A surfactant molecule has two distinct parts. The head of the surfactant molecule is hydrophilic, capable of attracting or combining the water, so it's water-loving, the hydrophilic. And the tail is hypophilic. Please highlight. The tail is hypophilic, having an affinity for the attraction of fat and oils, so it's actually oil-loving, hence the lipo. Following these, please continue highlighting. Following the like dissolves the rule. The hydrophilic head dissolves in water, and the lipophilic tail dissolves in oil. And to highlighting. So a surfactant molecule mixes and dissolves with both oil and water, and temporarily joins them together to form an emulsion. In an oil and water emulsion, so O/W, oil droplets are emulsified into water. The droplets of the oil are surrounded by a surfactant molecule with their lipophilic tails pointing in and their hydrophilic ends pointing out. With the heads pointing out, the tiny oil droplets from the internal portion of the O/W, oil and water emulsion, because the oil is completely surrounded by water. Oil and water emulsions do not feel greasy as oil and water emulsions become because the oil is hidden in the water forms and the external portion of the emulsion. There's also oil and water with emulsions. So the last one was OW. This one is WO. So it is the water droplets that are emulsified in oil. The droplets of the water are surrounded by the surfactants and their hydrophilic heads pointing in and their lipophilic tails pointing outwards. You can see that on figure 12-11. Tiny droplets of water, moving on to page 263. Tiny droplets of water form an internal portion of water in oil emulsion. So your W/O emulsion, because the water is completely surrounded by oil. Water in oil emulsions feel way greasier than oil in water emulsions because the water is hidden in the oil form and the external portion of the emulsion. Styling creams, cold creams, and foot balms are great examples of that. Other physical mixtures. Ointments, pastes, pomades, and styling waxes are semi-solid mixtures made with any combination of petroleum jelly, oil, and wax. Powders are physical mixtures of one or two more types of solids. Off-the-scalp powdered hair lighteners are physical mixtures. These mixtures may separate during shipping and storage and should be always thoroughly mixed by shaking the container before each use. Common chemical product ingredients. Cosmetologists may use chemical products when performing client services. Following are some of the most common chemical reactions used in the salons. Moving on to page 264. Volatile alcohols. Those that evaporate easily, such as isopropanol alcohol, so your rubbing alcohol, and ethyl alcohol, which is your hairspray and also in alcoholic beverages. These chemicals are familiar to most people, but there's many types of forms of alcohol, from free-flowing liquids to hard, waxy solids. Fatty alcohols, such as cetyl alcohol, are non-volatile alcohol waxes that are used as actual skin conditioners. Alkylamines are alkaline substances used to neutralize acid and raise the pH of many hair products. They are often used in the place of ammonia because they produce less odor than ammonia does. Ammonia. It's a colorless gas with a pungent odor that is composed of hydrogen and nitrogen. It's used to raise the pH in the hair products and allow the solution to penetrate the hair shaft. Ammonia hydroxide and ammonia thioglycate are examples of ammonia compounds that are used to produce and perform chemical services in the salon. Moving on to glycerin. Glycerin is a sweet, colorless, oily substance. It's used as a solvent and as a moisturizer in skin and body creams. Also, we use it a lot in our photo shoots. Please highlight silicones. Silicones are a special type of oil used in hair conditioners, water-resistant lubricants for the skin, and the nail polish dryers. And a highlighting. Silicones are less greasy than other oils and form a breathable film that does not cause comedones, so your blackheads. Silicones also give skin a silky smooth feeling and great shine to hair. Certain silicone resins, so silicone gums, can withstand super high pH environments and can be incorporated into relaxers and permanent wave formulations. Lastly, we have volatile organic compounds, the VOCs. They're compounds that contain carbon, organic, and they evaporate super easily, so then they're volatile. For example, a common VOC is used in hairspray. It's SD alcohol, ethyl alcohol. Volatile organic solvents used as ethyl acetate and isopropanol alcohol are used in nail polish, bases, top coats, and also polish removers. Let's move on to the pH scale. I think we all remember this from science class. The pH scale is actually known as potential hydrogen, and let's learn how it affects the skin and nails. Although pH is an abbreviation for potential hydrogen, it's often mentioned when talking about salon products, and it's one of the least well understood chemical properties. Notice that P is written small, and that represents the quality, and the capital H represents the hydrogen ion. The term pH represents the quantity of hydrogen ions. Understanding pH and how it affects the hair and skin and nails is essential to understanding salon services. For more information about pH products used in salon services, you're going to learn about it in Chapter 15. More about the shampoos and conditioners. And then again in Chapter 20 when we start talking about chemical texturizing services. Moving on to page 265, water and pH. Before you can understand pH, you need to learn about ions. Please highlight. An ion is the atom or molecule that carries an electrical charge. Ionization is a separation of an atom molecule into a positive or negative ion. The ion with the negative electrical charge is an anion, with the ion with a positive electrical charge is a cation. And a highlighting. You need to know the anion and cation in ionization. In water, some of the water H2O molecules naturally ionize into hydrogen ions and hydroxide ions. The pH scale measures these ions. The hydrogen ion, H+, is acidic. The more hydrogen ions that are in the substance, the more acidic it will become. The hydroxide ion, the OH negative, is alkaline. The more hydroxide ions there are in a substance, the more alkaline it will be. pH is only possible because the ionization of water. Only products that contain water have a pH. In pure distilled water, each water molecule that ionizes produces hydrogen ion and the hydroxide ion. You can see that on figure 12-2. Pure water has a neutral pH because it contains the same number of hydrogen ions and hydroxide ions. It has an equal balance of 50% acidic and 50% alkaline. The pH of any substance is always a balance of both acidity and alkalinity. As acidity increases, alkalinity actually decreases. The opposite is also true. Alkalinity increases and acidity decreases. Even the strongest acid also contains some alkalinity. Let's move on to the pH scale. Please highlight. The pH scale is a measure of the acidity and the alkalinity of a substance. It has a range from 0 to 14. And the pH of 7 is considered a neutral solution. The pH below 7 indicates acidity, so an acidic solution. And the pH above 7 indicates an alkaline solution. Please look at figure 12-13. The term, continue highlighting, the term logarithm means multiples of 10. Moving on to page 266. Since the pH scale has a logarithmic scale, the change of one whole number represents a tenfold change in the pH, so it would be times by 10. This means, for an example, a pH of 8 is 10 times more alkaline than the pH of 7. A change in a whole number represents a change of 10 times, or a 100-fold change. So pH 9 is 100 times more alkaline than the pH of 7. Even a small change in pH scale represents a large change in the pH. Please note, only substances with water can actually have pH. So even if you want to note that, would be great. Again, only substances with water can have pH. Moving on to pH is always a balance of both acidity and alkalinity. We're talking about the water now. Please highlight. Pure water has a pH of 7, which has an equal balance of acidic and alkaline nature. Please continue highlighting. Although pH is neutral at 7 on the pH scale, it's not neutral compared to the hair and skin, which has an average pH of 5. And a highlighting. Pure distilled water with a pH of 7 is 100 times more alkaline than the pH of 5. So pure water is 100 times more alkaline than your hair or skin. The difference in pH is the reason that pure water can cause hair to swell, as much as 20% of the reason that water is drying to the skin. Moving on to acids and alkalis. All acids owe their chemical reactivity to the hydrogen ion. It's pretty important. Acids have a pH level below 7. Please highlight alpha hydroxy acids, your AHAs, derived from plants, pretty much fruit most of the time, are examples of acids used in salons to exfoliate the skin and help adjust the pH level of a lotion, conditioner, or cream. And a highlighting. Acids also contract and close the hair cuticle. One acid is, please highlight, thioglycate acid, a colorless liquid or white crystals with a strong, unpleasant odor that can be used in permanent waving solutions. Please highlight. Glycolic acid is an alpha hydroxy acid used as an exfoliant and lowers the pH of products. And a highlighting. Please highlight. The alkalis, also known as bases, so please star bases, This is, we use these a lot, owe their chemical reactivity to the hydroxide ion, and a highlighting. They are compounds that react with acids and forms of salts. They have a pH of above 7. They feel super slippery and soapy on the skin. They often swell the hair and skin, the cuticle on the nail plate, and also on callous skin. Please highlight. Sodium hydroxide, commonly known as lye, is a very strong chemical of an alkali used in our chemical hair relaxers, callus softeners, and also drain cleaners, and a highlighting. These products may be used according to our manufacturer's instructions. It's very important that you do not let those products sit or touch the skin, as they can cause injury to the burning sensation on the skin and cause a chemical reaction on the skin and a chemical burn. Sodium hydroxide products may be especially dangerous if they get into the eyes, so always wear safety glasses to avoid the contact. Always look at your MSDS or your SDS sheets for more information on that use. Moving on to page 267. The same reaction that naturally ionizes water into hydrogen ions is hydroxide ions, also runs in reverse, if that makes sense. Please highlight. When acids and alkalis are mixed together in equal proportions, they neutralize each other to form water. You can see that on figure 12-14. Neutralizing shampoos and normalizing lotions used to neutralize hair relaxers work by creating an acid-alkali neutralization reaction. Liquid soaps are usually slightly acidic and can neutralize alkali to, callus softener residues left on the skin after rinsing. So how's all this actually going to help you in the salon? How chemistry is going to help you in the salon? Whether you're studying the pH of products, redox reactions, suspensions, solutions, and emulsions, there's a lot to learn about how chemistry affects the products you use and in the salon. Having a basic understanding of chemistry will help you as a professional with professional products and using them effectively and safely in the salon. Moving on to page 268. I want you to finish your review questions. Utilize your study tools by going through your study guide and also your exam review prep. We'll be doing a full class study on this tomorrow in class. I look forward to seeing you and moving on to our next chapter.